Thank you very much. From what I heard, just a little bit, I think it's very interesting presentation, but I missed it because I wasn't here. I was sorting out things in the background. But then my point is, I want to understand a little bit more if you guys work with sensor or monitoring the farming, because I know, like you said, you guys are not researchers. You're working more in monitoring. So that means that we can look here a way of combining. If my work is in research, you guys are monitoring, would be interesting if we could do some joint, some joint projects. Can somebody give me some water?
Yes.
Thank you. Sorry about that. Combine, doing some joint project, because I think it looks very interesting and it's jeopardizing. You have to go to France to do the research when we can do it here, and then we are agriculture potential countries. So I think it's a time that we should join and then do it here. So I don't know what you think about doing a joint project with ISPTEC. Here in ISPTEC, I know that there are people that relate to agriculture, but my person, I have some project that I've always been looking for people that work with sensor. So I feel like this is the opportunity for me to be able to join a project. What do you think about that? Well,
okay.
It's not really a question.
It's a discussion.
Yes.
It's a discussion. Maybe to save the time, we can...
So, yes. Yes, Professor, this is the reason we brought this presentation, is really to provoke, and I think with President João Fernando, I believe, and we discussed a little bit, I believe we will push this as well to see how we can work with ISPTEC. So you're right, so if we went to France in order to do research with them, we publish papers. And I believe ISPTEC is just around the corner. It's actually 5 minutes from our headquarters. So I think the idea is we can transfer all this experience to ISPTEC and collect, as you say, the research-based census experience as well. Because as I said, we still have next steps for the project and to be deployed. And this is just a piece of what we're doing. This is much bigger. We are now working with the European Space Agency as well on a model that will be a statistical tool officially for census in agriculture in Europe. I think it's a huge opportunity if ISPTEC want to come aboard. I think in Africa they were selected only 3 countries, and we, GGPN, are representing Angola in this project.
Okay, thank you, Dr. Zolana, for the answer. I would like to receive Professor Teresa Matoso, but before that, I would like to read a little bit about our background. I remember recently I was in India and they asked me, do you know Professor Teresa? Today it will be good to present her. Professor Dr. Teresa Matoso Mangwangwa Vitor is an Angolan or is Anglo-British. Is an Anglo-British professor, scientist, and engineer who excellent in the area of chemical engineering, process, intensification, polymer and catalysis, microbiology, and renewable energy. She holds a PhD in chemical engineering from the University of Newcastle, Upton in UK. Since 2008, She was involved in a multidisciplinary project in the intensification of antibiotic. Like myself, my field is a medicine. I have a PhD in medicine. But when we talk about the antibiotic, what we knew before, just Alexandre Flagman. Now, knowing that we have Angolan like Professor Teresa Matoso, who made a great improvement in antibiotic, is a great thing for us. If I was you, I was supposed even to plow before the time. Antibiotic producer using micropolymer with Professor Galip Akai and Professor Alan Ward as a supervisor. This inherent material resulted publication in prestigious journal with high impact factor. She also completed a master's degree in sustainable chemical engineering at the same institution in Newcastle. That it was in 2004. She graduated as a BS honor in chemical engineering, attended at Northumbria University, Newcastle, in UK, with the petrol refining and fraction distillation unit project. That was in 2001. In 2009 to 2014, she worked as a research associated at the School of Chemical Engineering and Advanced Material at the University of Newcastle. She was working as a processor and product development engineering at Nutris Ltd in UK. Since 2004, among of her many responsibilities were the production and functionalization of microscope material for the agro-bio process and the separation process, preparation, and presentation of proposal for scientific project management, knowledge transferable dossier with view its making and commercialization. She is currently a lecturer and research at ISPTEC since 2020, where she lectures and supervises undergraduate students. Okay. And she's also a member of the Senator and a life member of the World Research Council and accredited review for the American Journal of Chemical Engineering and invited speaker in several international scientific conferences. That means if you are publicating your article in American Journal, make sure it's not going to be refused because she's there. Let us continue. It's a little long, but it is important to understand who is our speaker. Dr. Victor has received several condecorations and distinctions for the innovative and relevant work for the scientific and the technological development of Angola and the world. Among the order of civil merit of the 8th degree, graduated by President of the Republic of Angola, João Manuel Gonçalves Lourenço, for relevant achievement in favor of the nation, the internationalization, best research reward in area of chemical engineering and biotechnology, graduated by International Society for Scientific Network and the Congress of Science and Technology. In 2022, the International Innovative Scientific of the Year Award for the Research and Academic Excellence in Chemical Engineering Award by the Astra Asia Science, Technology and Research Award Congress of 2023, and the International Outstanding Research Award for Research and Excellence in Chemical Engineering and Biotechnology, awarded by ISSN International Science Technology Award Congress in 2023. EESTAC 2003. I believe the achievement of our professor is long, but due to the time, let us to stop here. We can put our hand together to us, Professor Dr. Teresa. Please, podes applaudir bem. O breakfast foi bom.
Thank you, ladies and gentlemen. It's actually a great honor to hear all this presentation about myself, so I'm going to skip presenting myself because everything has been told already. So I'm going to go straight to the presentation. But before that, I would like to thank Dr. Marcilio and the whole team of Quantum Technology for inviting me in this prestigious ceremony, and also the fact that it related so much to the work that I've been doing for more than 2 decades. This work that I'm going to present here actually wasn't myself that I chose the topic. It was Dr. Marcilio that chose the topic. He went to my CV and took that topic. Luckily, it's a topic that is already being patented. Okay, thank you. So as it says there, let me see if we point and then read it together. Synthetic symbiotic system as a soil additive to deliver active ingredient through the plant roof for enhanced plant and crop yield. That's what we're talking here about. Finish the hunger. So it's about improving the crop yield. So then the previous presenter, they were talking more about sensors and they talk about water shortage, but all we need, apart from water shortage, we need also to improve the soil because the plant need, apart from the water, need the soil. So that's basically what I've been doing all these years. So as it says there, symbiotic reservoir simulated, although in the title you say SSS. Here we call it for the normal day, symbiotic rhizosphere simulated, because we simulate the rhizosphere. The rhizosphere is the region where the plant lives, where they find all ingredients, nutrients that they need. So then we simulate, instead of say synthetic, we're simulating. And the rhizosphere, and symbiotic, because in that area will create a symbiosis between the plant, the microorganism, and the nutrients that are there. So basically, we come up with this material, which is a polymer material, but let's not think that all polymer, they're bad. This is a polymer, but we functionalize it, and it stop being harmful like the normal polymer. Are you with me? So we created this environment to improve soil characterization and provide with necessary ingredients that the plants need. Also, we design it to create a microscopic environment between the plant roof. And then we will see this during the presentation. And then we will see here that this material actually has a lot of property. So if we're going to put the plant, because we eat what's coming from the soil. So if we have a harmful environment, basically the plant will absorb and we eat that. So then the material that we are mimicking has to be what? Has to be non-toxic, has to be inert. And then if we want to improve the soil health, it has to be what? Hydrophilic, means that absorb a lot of amount of water for later to release to the plant. If it is a dry land, then means that when it's raining, the material will absorb fast and then release slowly when the plants need. And that is the big issue when we put the fertilizer, for instance. Not always the plant has the capacity to absorb those nutrients. So then when it's rain off, everything runs to the rivers, to the sea, to the water. So let's move to be able to see what I'm trying to say. I don't know what's going on. I'm sorry. So then I want to talk a little bit about the story of the invention. As you know, all started from 2005 to 2008 when I was doing my PhD. And during that moment, I was doing my PhD, a multidisciplinary PhD in the School of Chemical Engineering and the School of Biology. With like they've been said already, with Professor Alan Ward, which was for microbiology, and Professor Gali Pakai, which was chemical engineering. But during that study, you know, you don't decide that, okay, today I'm going to the lab and I'm going to invent something. There's some invention that happens by accident, okay? And I'll be honest with you, that's happened by accident. By mixing, by functionalize the material, I could see the material has changed. I was starting to swallow 13 times more water than its own dry weight. So then, as a student, I ran and I went to my supervisor and I said, Professor, look this material, because the previous guy that was working in the plant, basically his polymer were hydrophobic. You know what is hydrophobic? It doesn't like water. But for agriculture, you need hydrophilic. You need to love water. So then I made hydrophilic the material without even know it. So all happened then, what happened? The supervisor said, give it to David Berker, because David Berker was working in the plant. I was working what? In production of antibiotics. But for production of antibiotics, I didn't need very hydrophilic environment as the agriculture. So let's pass this story because it's a long story. Let's cut it short. I don't know what's going on. It's not moving. It's not moving, sorry. I'm not great in this technology because when I started it, there was no computer when I started to go to university. Yeah, it's not moved. Okay. Okay, then maybe I'm not pressing that much. This is just one of the patents, like I said, from this material, it was created 2 patents. One patent was for the material in various applications, including the application that I needed. And the other patent was as the one we're going to discuss today. Ah, this way. I'm pressing that way, you see? Everybody saw me pressing that way. You changed? Okay. Okay. I put it there if you would like to read it, but if you don't, we can pass it. But basically it's what I've just said it, okay? And then we have this strategy. And maybe some of you already heard about process intensification. It's more headed in chemical engineering, process intensification. It's a strategy that is being invented in the 16th. And I had the privilege to be a student of the person that invented this strategy, Professor Colin Ramshaw. Colin Ramshaw, he believed that with process intensification, you could reduce the cost, reduce some step in the process, and this will bring more economical advantage. So then what happened is we took that process intensification strategy to the agriculture. Basically, I've got here this image where you could see that this is the rhizophasic cycle. So what's happening is inside the plant. So when we produce the material, like we say, is they want to mimic the rhizosphere, then we add in some microorganisms that will be beneficial for the plant. Some of these microorganisms, they're endophytic. Then if they are endophytic, it means that they will go inside. They'll go inside of that design that we saw, and then the endophytic will go inside, will be helping the plant to fix nitrogen from the atmosphere. That's not great? So it means that if the plant needs nitrogen, we really can just fix from the atmosphere by using some endophytic bacteria. And then if the plant need potassium, also we can put some microorganisms that will make potassium available to the plant, or phosphorus available to the plant, because some of these components of the fertilizer, they're actually soluble in water. And being soluble easily can wash out, like I say, it can go to the river. So then if we lock them to this material, means that will be there available for the plant. It's not gonna be washed out. So all the project, we start with a problem. So there is a problem to solve. One of the problems just that the fertilizers get washed by the water. And then what we get water pollution. We get soil degradation. So then the problems are here. And then we need to address this problem. For example, we have here the red one supposed to be the light. Am I right? Yeah. No, the light I need to point to the presentation. No. Okay. Then we have here the river contaminated with heavy metals. No? And then we know what sensitivity as human activity is food agriculture. And that contaminates the waters a lot, not just the industry. Okay? And then we have here also soil degradation. When we have a... Okay, I rather move around. Okay? So addressing this challenge will be with what? Basically what I've already said, using our microporous material, because we lock all these ingredients and deliver when the plants need. You know, the first presenter is from the space, so understand better than I. It's not working. Can someone change for me over there? Okay. So this is the material. So we solve the problem, and then we find here the solution. What's the solution? Development of microporous structure material. That's exactly what I said. Known as a SRS, symbiotic rhizosphere simulated. That's what we said, no? Then that can be functionalized. Like I said, first is a polymer, but after we functionalize, actually when we functionalize, it stops being hydrophobic, it becomes hydrophilic. And the other properties that we're going to see later, because we will help then the diffusion of nutrients, the diffusion of mass transfer, heat exchanger will happen smoothly, because it actually resembles like a capillary network. You know, in our lungs, we have capillaries where oxygen can be transferred. So it basically resembles that. That's why we have this structure of a capillary. And that is the material. When we look in SEM, scan electron microscopy, we can see all the pores, and we can analyze what type of the pores we have, what size the pores we have. Okay. As already give you a little bit of the background about the material, then we need to produce the material. To produce the material, we need a reactor. Okay? And we know some of us here that is being a lecture of a reactor calculation probably they know, or even never been lectured, it being a work of a reactor. we know that the mode of operation for our reactor will be semi-continuous, although there is a continuous, semi-continuous, but here we want to use it semi-continuous. Semi-continuous because we will see when I show you the reactor, because we continue feed in, but the outlet, the downstream is locked, is closed. So we are only feeding, but we are not, until the reactions take place is when we open to collect our product. Then the reactor type that here we're going to use is the reactor non-catalytic. We could also use the reactor catalytic if we want, because we could use, for example, sulfuric acid to act as a catalyst. Number of a phase would be heterogeneous phase, because one of the phase, when we have 2 or more phase, then we have heterogeneous phase. Because not a homogeneous, not every phase is liquid or every phase is gas. Here we have, although they're both liquid, but one of the phase doesn't mix. And we know, for instance, when we put oil and water, they're not mixable. And then when oil and water are not mixable, what we do? We use the tank agitation, okay? So we use impeller to be able to mix the two, and the emulsion will be created. Basically, this is the reactor. As you see there, we have the vessel, we have the motor, we should make the impeller to work. We have the parastatic pump that will help us to pump the liquid to our reactor. Finally, we got our emulsion, and then we pour it to another reactor with 60 degrees. After that, what we do, we need to take it to the circlet, basically to wash, to remove all the reagent that hasn't been reacting. Okay? And passing now then to the properties, as you see there, as we saw before, then if we look in a scan, SEM, scan electron microscope, we'll be able to see everything that we can't see with naked eyes. That's why we managed to see that, oh, they've got big pores, what we normally call them coalescent pores. Coalescent pores, those pores that when you're mixing, small pores join together and then they make a big pore. So we don't want too many coalescent pores in our structure. The good thing of this material is that you can control the properties. You can control the pore size. You can control the surface area. And we know the surface area, if the surface area is big, means the pore size has to be smaller. It's inversely proportional. Then we have here, look after functionalization, we're going to look at the material in SEM again. Could we see some crackings? That's good. Those cracking means that even the soil, the natural soil, because what we're trying to mimic is the soil. Even the natural soil has crackings, so that means that there will be diffusion of what? Nutrients. The fusion of microorganisms that are in the environment. And that's what we wanted to achieve with the functionalization. And just to tell you that this material doesn't just have application in agriculture, has also application in tissue engineering. Like I said before, with capillary, it resembles what? The lung. The lung is porous. So it can be used for tissue engineering, even for bone tissue engineering, because the bone, it looks like a scaffold. If you, I don't know, if we cut the bone, cross-section, you will be able to see pores, and they resemble this material, so that we take it as well as a tissue engineering application. Intensify separation of oil and water emulsion is one of the work that my colleague from Malaysia, Zainura, has done, and the result was very achievable, and she was able to submit that as a chapter in one book. And then we have also intensified gas-liquid separation. We have the gas cleanup, which work done by a girl that was working gasification process. We have also water cleanup. A Turkish guy was working water cleanup using the same material. And then in catalyst, A lot of people were working using this material for catalyst. Basically, for catalyst, what we'll do, we just deposit the metal that we wanted this material, and then the catalyst will be microporous catalyst. That's good, because then when you calcine, all the material go away, and then you have the structure of the metal porous. And then we also work in microreactor. In that case, I was working the microreactor. I was working intensified bioprocess, which basically to be able to produce the antibiotics. And then finally is the agro-process intensification. David Becker worked on that, and that's also I work during my research associate. I work on that as well, and that's the part of the patent that we're discussing today. I brought you here this. I call it my Pulse diagram, basically to describe what we saw before. Basically, we have here the micropore in the middle, and then we have all these tentacles trying to go to different applications. In the health, we saw tissue engineering, production of antibiotics, and then we can go to agriculture, this case is symbiotic rhizosphere simulated. We can go to the environment, which clean up is a separation process, because we can use as a membrane for separation of process. And then energy is also, we can use it to immobilize microorganisms to be able to produce energy. And actually, the list of applications going on, because now being here in ISPTEC, one of my colleagues that is mechanic is actually said that we can do some work for mechanic application as well. So we are trying to test the resistance of the material to see if we can use it for mechanic purpose. Yes, then that's just to show that is the process intensification, like I said already, related to the agro-process, related to the process intensification. Application and the benefits, we have what? The SRS can be used for various crops, such as these crops that I put there, that's the crop that appear in the patent, such as cereal, leguminous, vegetable, fruit, and flowers. But in reality, when I came here in the ISPTEC, we also try with different crops. We tried with corn, we tried with tomato, we tried with okra, and we had our little greenhouse there at the back. I don't know, some of the colleagues probably remember, we used to have the greenhouse here where we're testing the material here in Angola. We didn't want just to have a result from the other geography, so we had to do it here in Angola as well. So during the process, like I say, is all the physiochemical properties can be changed. So basically, we can make it more elastomers, we can make it more porous, it depends on the application that we are interested. We can make it more hydrophilic or more hydrophobic, and so on. That is the beauty of work on this material. I think I'm never going to work another material anyway. So here, some culture that we test. As we saw, we test cocoa in Colombia. We test coffee in Colombia as well, and in England. So then there's some results. If you look at here, it's gone. Okay. If we look at here, the first plant, very small, that's without SRS, and it was the only one that survived. And the beautiful thing is, I wasn't the one doing all these tests. These tests were doing, like I said, in this geography, I wasn't there. So I was just sending the material for them to test, so to have a second opinion. I think that's the best way of doing things. And then you could see the biomass of the plant, a lot of growth of the roof. That is a sign that the plant is happy. So we are simulating the environment. Let's go quickly. Okay. Here, we did some testing in England of miscanta, because miscanta is like a grass, but it's a grass that used for biomass, for energy. And then it grows in cold countries, like originally from Poland. And then we grew it in England. We didn't manage in Bellsbrada to make some some Bell's Brothers a nursery where we do the plants, and then you could see there with the SRS, without the SRS, we could see definitely photosynthesis wasn't there when SRS wasn't there. So there's nothing really to say much. And then here we have different grasses as well that have been tested in different conditions, just with the blank without SRS, with SRS, only with SRS with Aspergillus. Aspergillus is another endophytic that fixes nitrogen, and then SRS with grass of a mycorrhiza. Mycorrhiza is a microorganism that grows in the rhizosphere, so normally making nodules to the roof of the plant. And then we have here banana that has been done in Indonesia and in China, but I didn't manage to get the results from China. Okay, I only got it from Indonesia, and we could see some of us, we don't know that the bananas, they're dying. Bananas, they're being affected by a fungus called 4-4. So if we don't solve this problem, there'll be a time that we're not gonna eat our source of potassium, which is banana. So then we could see, as you see, that it's being affected by fungus, and the inside of the stem is actually dark, and then when it's with the SRS, it's all clear. So the picture probably talks more than myself. Okay, this is some field trial in Colombia that has been done with palm oil, and then also with different conditions of SRS1, SRS2, without SRS, and without no doubt, the result with the SRS were much better. And I wasn't there again. Okay, and then also, like I said, with Mescanta, we did in Bell's Brother. Now Bell's Brother took to the field, because Bell's Brother first do the growth in the nursery, and then after takes to the field. What happened there in the field? You could see with SRS, this is the time of Everest. You Everest them when they're dry, because it's for making biomass for fuel. So then with the SRS, definitely, I'm not gonna say that much. You guys can see with the SRS, without SRS. Again, was a second opinion. I didn't done this test. Okay, this is the test that we did here in ISPTEC with the students. Some of my colleagues here remember that I managed to recruit more than 30 students from chemical engineering that they've already now finished. Some of them, they've already defended at TCC. And then we also, image can tell you what happened there. Although we are not from agriculture background, we try our best because we just wanted to test the material. Therefore, that's why probably the area wasn't very well organized the way it should be if it was someone that with an agriculture background. Then we also managed to have okra. I did eat the okra from here. I did eat the tomato. We planted also passion fruit. I didn't manage to eat passion fruit because the student, they took passion fruit. So it means that I'm still here, nothing happened. The result was good. So I'm almost finished now. That's just to show you how happily the roof hair are inside of the material. As we see there in the top of SEM, actually the roof hair penetrates inside the material looking for nutrient. And what is inside the material? There's nutrient, okay? And then that's why the plants grow happily. Then we can see here, this is grass association, how it looks. That's a soja. I brought soja from UK to grow it here in Angola, but I didn't manage to grow there with the student. Soja didn't want it to grow. Yeah, that's what happened. And then also here, we took an SEM, the SRS, we cut it to the cross-section to be able to confirm if the endophytics actually they were in the SRS or they translated to the roof hair. Because as we said, endophyte, they're meant to live inside of the plant, but they're benefic. They don't do harm to the plant. Actually helps the plant to fix the nitrogen. So then we confirm of the SEM, as if you see here in red, that's the bacteria that we inoculated that were inside. And then here we have some Mescanta result from Bell's Brad. where you see A and B, they are with SRS, and then control 1 and control 2 without SRS. So A, which was that tray that I show you without SRS, with SRS, was much, the growth was unbelievable. Was very tall, and we could see that photosynthesis took place. But then what happened? The leaves, there was not much difference in the leaves. The amount of the leaves, we couldn't see much difference. Can you see? So maybe the responsible of the leaves, because each nutrient in the plant has a responsibility. Some they're responsible for give good biomass in the roof, some of with the leaves, some of making the leaves very green. So responsible for amount of the leaf probably wasn't there in our material. Makes sense? But we could add in because it's very flexible, very versatile. So this is the ongoing work that we are doing here with the resistance of the material in the lab with colleagues from mechanic. So we're trying to take it there, the young module, to see the elasticity until by putting force to the material until when the material will break. And I hope this will give us a paper to be able to publish our work. I think we just finished. This is just the conclusion, which I'm not going to say the conclusion because I've been saying it as I was going. So then, just to show you finally some references that became from the work. Yeah, that is the reference that came from the work. And then finally, okay. That is the letter that I received from Newcastle University because there was a problem with my second patent. My supervisor put David Burke in the patent, but he never put it me. And then in 2014, when he left, I had to be with the responsibility to do the work that he was doing, to submit all the work that he did. In my research, I discovered this patent. I read through the patent, and I could see all the clauses. That's the one that I wrote to give it to him, but he didn't include my name. But in God's grace, I won the case, and they included my name. So it means that when the patent was filed, my name wasn't there. But when the patent was accepted, my name was there. Thank you very much.
Professor, you can take a seat. And you can also hold the microphone.
Sorry, I'd like to thank for the support that I received, because without the support from the UK government, nothing this could have been possible, because my PhD, my undergrad was from Angola government, but my PhD was from British government. So thank you very much.
Wow. Okay, let us go straight away without of mixing with Professor Americo question. If you have a question regarding Professor Teresa Matoso, we can ask straight away. Myself, I have 2 questions, but I would like to collect yours. Okay?
Good afternoon, Doctor.
Good afternoon.
I am José. I would like to speak in Portuguese because I have a little difficulty to speak in English. Can it be?
But can you understand? Feel free. This workshop is in English. If you want to challenge your English by yourself, continue. Even with mistake, this is the way of learning.
Yes. No matter. I would like to relationship about the pH. pH is the most important property of soil, is plant. I would like to relationship to pH. Yes.
Yes.
Yeah, about the impact of the environment. Yes.
Okay.
Please, we can applaud for Mr. Jose. You did well. We understood what you wanted. This is the way. Well done.
Thanks so much. Thanks.
This good question. But if you remember when I said that we mimic the natural environment, that means is mimicking for everything, including the pH. That's the pH you refer pH, no? pH, including the pH. So if we are mimicking and we know in the normal environment the pH that the plants grow is a 6.9 or 7, then means that our material, we need also to adjust it because we say it's versatile and we can easily change its property, including pH. Okay. But then with the pH, we need to be careful which base we're going to put because we don't want to mess about putting sodium hydroxide because we end up to leave a lot of sodium. Okay. So then, what is the base, the acid, the base that we're going to use? Probably we use ammonium hydroxide. Because whatever result is, will be what? Salt and water. Ammonium sulfate plus water. Am I wrong? Chemical. In the chemistry point of view, you don't want the result to be harmful to the environment. Because what we're trying to do is solving the problem of the environment so we can't bring another problem. Okay?
Okay, thank you very much, Professor. Let us go to the second question. I hope that Mr. Jose is clear.
Are you happy?
Are you happy? Good.
Mr. Desiderio, once again. So I could like thanks the beautiful presentation that we all saw. So my question is, all that country that you send the sample, I could like see during the presentation, they are all tropical countries like England, Thailand, and China,
England.
I saw. England.
England is not tropical.
It's not tropical?
No.
Is it cold?
It's the cold. Yes. But my question is, did you send some kind of sample in different environment like desert? So here in Angola we have Namibia province. The environment in that province is like a desert. I could like understand if we have some kind of study in this area.
Yeah, that's good question. That's good question, and then because what was in our plan? I did my PhD, I invented this material, but then after finishing my PhD, I was then work as a research associate. That means that I continue to do some investigation this work in Newcastle University. So then, because Newcastle, England is not a tropical country, so then we had to start to send sample to a tropical country until I got tired and I say, my country is also tropical. I'm going to take the technology to my country, okay? But there was the purpose of sending the samples to Dubai because Dubai wanted to grow grass. That's why we had some experiment trying to test in the grass. So it means that in the nursery, we could see that the grass grows happily in our material. So that means the next step could be field trial, send it to Dubai. But then what happened? My supervisor stopped working for Newcastle University, and then the project died there about taking the sample to Dubai to try to the desert. Okay? So, but the question is very good, because then you open me my window, because we have desert here in Angola. Yeah. Where can I go? You made me you clicked something that was dying, or wasn't dying, was sleeping, was domed. So now you click it, I'm going to do that. Thank you for your question.
All right.
Thank you very much for helping to the resurrection of something which was dying
Yeah.
to Professor Teresa Matoso. One more question. Okay. I have just small question, Vice President. Professor, you say that you brought some soja from Newcastle, but it could not grow in Angola. Why?
I don't know. And the student should be here to answer. Maybe the environment of that soldier, or maybe that soldier was genetically modified, and then growing things genetically modified is more complicated than growing things that are not genetically modified. Because non-genetically modified, they grow like, let's see, like Jimboa. Easily they grow, you know? But when they're genetically modified, means that you have to follow pé da letra, como se diz em português, all the steps for this. Then since I didn't have the protocol to do it, we were just doing it here in this ISPTEC with the student. And I said to the student, let's try again. And then he said, professor, I didn't grow. I said, let's try again. Hey, professor, mesmo gosta da soja dele, until the soja go rotten. So if it go rotten, if before go rotten it wasn't grow, after go rotten, what's the point to put it in the soil?
That's fine, Prof. We understood it did not grow. And also you said that you planted something, the students, they eat it without of giving you. I don't know why.
It was a passion fruit. And even my colleague was here, that she's from, she's a nurse. One day she sent me a photo. Professora, your passion fruit is actually growing beautiful, but I wanted to take it to give it to you because I know you are doing it for research, but it's still a little bit green, but it's big. I said, let it stay. But professor is gone.
I ate it.
I don't know, the student or another staff took it.
Okay, let us put our hands together for greater presentation. Thank you very much. I hope that you will come back to the next time when Dr. Masil is going to host another event similar to that.
But then what I would like to see here is actually the symbiosis, the multidisciplinarism about our project. Because when I won the prize, my first appeal that I was doing to everyone that I wanted to work with a census. Now today I hear here that you guys work on the census, so nobody answered me in that moment that, yeah, we can work. But now that we are face to face, you know when you're speaking to someone face to face, you can't say no. So what I wanted to see is us joining together and do a multidisciplinary project for production of antibiotics, for agriculture, for catalysis. All these things need census. Thank you very much.
You're welcome. Thank you, thank you. I hope that you are enjoying it. Teresa, please.
Hello, yes, Dr. Mark. It was a very
Hi.
interesting presentation, but you're going to answer something for someone that doesn't have any experience in quantum physics. So I just wanted to know if you guys have calculated the energy consumption of your equipment.
Yes.
Okay.
Yeah. So we actually, this picture here at the top right has a little, let's say, hint at what energy we're expecting to consume. So we're limited by what solar power we can get. So the solar panels here are covering the whole spacecraft because we want to get as much as we can. And so it is a big push on our side to try to reduce the energy consumption. So we're talking down to like 100 watts or something like that at a time. So it could be that we store up the power when we're facing the sun and take measurements later, but it sort of depends upon exactly what we want to sense. So we will be using some form of batteries in the missions.
Yes, because that could be my next question. What about in the day when there's no sun?
No sun in space?
Yeah.
Well, luckily we're orbiting at about a 90 minutes sort of period.